Teresa.
And Manja.
Today's video is on
Reaction rates.
So today we've been discussing reaction mechanism and of course been discussing reaction speed. So let's measure that speed of a reaction and we'll call that the rate. So in order to measure the reaction rate, we need to quantify it in terms of some observable property of the reaction as time passes along. It's best if you can actually measure this property rather than just observe it, because then we can quantify the rate in some kind of tangible unit. For instance, let's look at this reaction here, the combustion of methane. This reaction, once we have it balanced, you could see that mass of carbon dioxide would increase as time passes along, or perhaps the mass of methane could be consumed and so on, and we can measure these things as time passes. Another reaction, perhaps this is the decomposition of hydrogen peroxide. You know that it makes water and oxygen gas. Once you have that reaction balanced, we can see there, what happens when you decompose hydrogen peroxide and try to measure its rate? Well, here's the reaction. Remember what this looks like. You have some bubbles of oxygen gas being formed there and the hydrogen peroxide in the flask decomposing. So if it's in an open container, you could measure the mass. Obviously, that would decrease as oxygen would leave the system. In a sealed container, perhaps you could measure the pressure, and so on. In every case, it depends on the reaction. If you want to measure a rate, you have to see the actual situation of the reaction you're looking at. So let's see some options. 1, you could measure the moles or the mass of reactant or product present. You could measure the pH, perhaps the concentration of a solution. Of course, you need special equipment for this. You might measure a color change. Perhaps a colorimeter would help you to do that. You could also measure the conductivity change of the solution. You would need a conductivity meter for this. Perhaps the pressure of a gas system. Of course, to measure pH, you need a pH sensor, and a balance might help you do the moles or mass. You need a pressure sensor if you want to measure pressure, and to do temperature, you might need a thermometer or even a digital temperature sensor. And of course, there are other choices you have too. These all depend on the reaction. If you got that message so far, it really does matter what the reaction is. Now, we're usually concerned with average rates. So let's look at combusting a candle. Here's the mass of the candle will be on the left and time will be on the right. Candles burn at a relatively constant rate, and so this relatively constant or steady reaction shows you a nice straight line here. And this slope, that would be the change in time. Here we have the change in some property, say the mass of the candle, for instance. We would say the rate of this was equal to the change in the mass versus the change in time. But most reactions don't really behave like a burning candle, which was very steady. Here's a reaction that behaves differently. This is back to that decomposition of hydrogen peroxide again. Have a look what happens. Again, we remember here the hydrogen peroxide decomposing into water here and oxygen gas. And heat. Now, this reaction here is heat sensitive. So at the beginning it starts slow, the reactants are cold, then it gradually speeds up. As it gets going faster and faster, it hits a maximum rate and then starts slowing down as the concentration of the hydrogen peroxide itself declines. Eventually, the mass stops changing and the reaction is complete. This is also not a typical reaction. You can see these are the instantaneous rates at any moment in time. They're the tangent lines on those points, and you could just take the slope of them to get the instantaneous rates at those times. Or if you're interested in the average rate, as we mentioned before, you could take it from one time to another, say from 0 to 10 minutes, and get the slope of that line. It's the secant line between the two times of interest. So that would give you the average rate over that interval. So here's what we usually see more frequently. Here's a sort of more typical reaction. This one here will be the concentration curve on the left, time on the right, and this would be the single replacement reaction with zinc and copper sulfate. You see copper would be formed here and zinc sulfate would be formed. You have a high initial rate because the reactants are initially at a high concentration, and later the rate will decline as the copper ions decrease in concentration, and eventually the concentration of copper ions will stabilize. Now we can also use unit analysis to help us work out some details about rates. Let's see what that looks like. For instance, here's an example. This reaction is between calcium chloride and sodium hydroxide, aqueous solutions forming calcium hydroxide in precipitate form and sodium chloride. Well, if 2 liters each were poured together and they were 1.5 molar apiece, and this reaction completed in 2.5 seconds, how could we express the average rate? Well, let's try to express it first as a mass of calcium chloride consumed per second. Well, little unit analysis will get it to you. It's clearly 3 moles of sodium hydroxide that are formed. There's 2 moles of sodium hydroxide for every 1 mole of calcium chloride. Here I have the molar mass of calcium chloride. And finally, divide that by 2.5 seconds to make a rate. Check that all the units work out, and you get grams of calcium chloride per second. There's one kind of calculation. Here's another thing you might like to calculate. Perhaps it's the change in concentration of the sodium chloride per second. Well, 3 moles of sodium chloride are produced. They're in 4 liters, so that's 0.75 mole per liter, and that happens in 2.5 seconds. So a little bit of calculations of the units here, and you see that this reaction is changing at 0.30 molar sodium chloride per second on average for those 2.5 seconds. So let's summarize what we've got here about rates. First of all, there's that idea of instantaneous versus average rates, secant versus tangent line. Be careful with those. Second, the idea that we have to monitor some measurable aspect of the reaction. Something you can monitor in real time is best. Finally, you can use unit analysis to do some calculations if you want to, and make sure that you understand the factors that increase rates of reactions. So that's about it for reaction rates. Thanks so much, and see you soon. Please make sure you have a look at the next 2 videos in this playlist for more on the topic, and stay tuned for the next lesson in Chemistry 12, Lesson 6, Enthalpy Diagrams.
This is my dad's YouTube channel. It's awesome. So like, comment, and subscribe.